Hello, good morning everybody. So we are still continuing with phosphorus, where we'll be basically talking about that industrial part of phosphorus chemistry. So industrial phosphorus chemistry. So we'll be concentrating on that, and already we have discussed about the getting of P4 from the mineral source, and from there we have reached up to the industrial preparation of phosphoric acid and the different corresponding salts. So if we consider that we are concentrated our attention on the inorganic chemistry of phosphorus and how we can apply that for making large amount of different types of compounds. So making all these phosphorus based compounds tell us that we can have these different salts also, and these salts are very much useful. So we are categorically discussing about their applications. And in doing so, whatever application it can have and whatever importance in the market and the industry, we should never forget about the corresponding basic chemistry what we can have, because this phosphorus, as we all know, that this P4 molecule is very interesting one, and this basically this particular one, the tetrahedral P4 molecule what we can have. And if we can get it from the mineral source like that of our apatite, we can get this P4, and P4 can be converted to some other forms what is useful as your corresponding phosphorus compound. So mostly in all these cases, after getting this phosphorus or the elemental source of phosphorus or nitrogen, whatever it is, we basically focus our attention on the different compounds. So these different compounds, one such will be definitely the corresponding acid salts. So once we get these acid salts, and if this is acid, and whether we can get these as the corresponding esters or not, we will see this. Because while knowing the corresponding organic chemistry such as that of our acetic acid or any other thing, we know that how we get the corresponding organic acid esters in our hand. So similarly, if we can get that from the inorganic sources, we can put some organic alcohol to get the corresponding acids as the esters of all these phosphoric acids. So that we'll see here in terms of the corresponding compounds what we can have, that some of these compounds, they are very much useful. So in terms of their application, if we see that these applications what we can get is therefore that use of cyanide, non-cyanide electroplating in dyeing and refining of clay. What are those compounds which will be useful for this purpose? So it's basically a tetrapotassium diphosphate compound, and how we will prepare that. So what we can have by knowing the name of that particular compound, we should be able to tell that it is not a simple phosphate salt, is a diphosphate salt. So two phosphate units, because these phosphate units are always very interesting. Today we will just simply cover from all these to up to some very deadly or lethal nerve gases also. So phosphorus based compounds in all the different types we will just try to understand or try to see how they are prepared. So if we get the diphosphate preparation, so diphosphate preparation is dependent on some reaction where we can get it as the completely all these things as the tetrapotassium salt. So tetrapotassium diphosphate preparation would be useful in terms of their uses. So the second category of uses are they can be used as analytical reagent or analysis reagent. So they can be useful for some gravimetric reagent, such that if it can give you the corresponding diphosphate for the metal ions, because as you see from the tetrapotassium diphosphate thing that you have these potassium ions already. So if we can go for substitution of those potassium ions by some other metal ions like calcium, magnesium, even lead and all other thing. So we can get the corresponding salts as the diphosphate salts of those metal ions. So it can function as an analytical reagent for that purpose, and it is also a stabilizer. The potassium salt, which is highly soluble in water, last time we have seen that this can have the 4 negative charges when you have the 4 K plus ions in it. So it will have it is highly water soluble. So it can be a stabilizer for hydrogen peroxide, and as well as sometimes it can be used as in soap as the filler material. Why we can get these things? Because we'll see at some point, because one of the most important compound in our industrial sector is that of your not diphosphate, it is the sodium triphosphate. So that sodium triphosphate can function initially when it was discovered long back, about 70 years back during 1947. People tried this for as the substitute of the soap material. Soap, we all know, they are basically another kind of surfactant molecules, the anionic surfactant molecules. So these are very long chain fatty acids, sodium salts of long chain fatty acids. So these can be substituted by these phosphate based materials, which can be considered as the detergent material. So the whole industry of detergent has flourished after that during the discovery of that thing. So it can therefore be a filler. So the pure form of these salts, the trisodium, that is triphosphate salt, is your detergent material, but this diphosphate salt can be utilized for filler material for the soap. Then in the third category, it can be used as emulsifier, it can be used for texturizing agent, that means it can improve the textures of the textiles or the cloth material or the paper or any other thing where we can try to improve the texture, even the metallic surface also. If we improve the texture of that metallic surface, we can use it as a texturizing material or texturizing agent. And then the chelating agent for the food industry. Why we go for the chelating agent? Because we know that a very useful chelating agent that we can use for our analytical sake or analytical purpose is the ethylene diamine tetraacetic acid, which can bind very nicely the available metal ions like calcium and magnesium in hard water. So if all these metal ions or some other metal ions are also present in the food material, so if we want to trap that for all these things to improve the quality of this food material, we use these as the chelating agent or chelating agent to trap those metal ions in the food industry or the food material. So what we can do is for this preparation, so diphosphate preparation as the tetrapotassium salt, we will use dipotassium hydrogen phosphate. In our previous class, we have discussed in an elaborate fashion that how we can get the different types, that means at least 3 types, the monosodium, the disodium and the trisodium salts of phosphoric acid. Similarly, the dipotassium salt of phosphoric acid gives us the corresponding K2HPO4 as the salt. So we can get it from directly from the acid medium giving potassium hydroxide or potassium carbonate or potassium bicarbonate. So to get this one, that means it's basically a condensation reaction between 2 phosphate units, which can be achieved at a temperature of 350 to 400 degrees centigrade. That means if you grind it and make it a powder, and if we put that powder in an oven and that particular oven is maintained at a temperature of 350 to 400 degrees centigrade, then as the basic reaction at that particular temperature, the condensation of 2 phosphate units do take place for that particular case to give you the corresponding K4P2O4 species and the elimination of 1 water molecule. So that is the thing that we basically remove, that is basically some kind of dehydration reaction, a high temperature dehydration reaction at a temperature of this range. So we basically get the corresponding diphosphate as a tetrapotassium salt, and this will be very much useful for the different purposes. So we can get also the other salt like that calcium phosphates. How we get these calcium phosphates, that is also very interesting to know, that getting calcium phosphate is also in a similar fashion directly from the phosphoric acid material. So if we use instead of calcium hydroxide or any other calcium salt, you can use simply the calcium oxide which we get from limestone. So, the source is also known to us and is cheaply available. So, that calcium oxide, when it is directly utilized for its reaction with phosphoric acid, we can get the calcium salt as a typical one for is CaH2PO4 whole 2, or a 1:1 reaction will give you a calcium hydrogen phosphate in our hand. So, this particular calcium phosphate, like that of our tetrapotassium diphosphate salt, is useful for getting it in the form of a baking powder, because one of the constituent of the baking powder is your monocalcium phosphate or the CaHPO4. And also in toothpaste, so toothpaste also we use the calcium hydrogen phosphate dihydrate. So, calcium hydrogen phosphate and its dihydrate like that of our gypsum. Gypsum is calcium sulfate with 2 water molecules of crystallization. Similarly, here the corresponding salt as the dihydrate salt, if we get, that can be useful for our making toothpaste. So, along with all other constituents, one of the constituent is your corresponding calcium hydrogen phosphate dihydrate as a toothpaste material. Similarly, we can have the dicalcium phosphate, which does not react with fluoride, it utilized in the fluoride containing toothpastes also. So, other phosphate salts can also be utilized in case of making other types of toothpastes. So, like that of our dipotassium or disodium salt, if we can have the di or polyphosphates, and it can be a typical calcium salt. Why we are considering this calcium salt? Because as just now I told you that calcium and magnesium, which are the basic constituent for your hard water, and the entrapment of that particular material, that means the entrapment of this calcium as EDTA for the corresponding complex of calcium EDTA to remove it from the hard water, which basically removing the hardness of that particular water sample. In a similar fashion, if we can use directly that particular diphosphate for trapping calcium, so we can get the corresponding salt like that of your tetrapotassium salt. We will also see the tetrasodium salt, which is also very much useful. So, this particular one, that means the Ca2P2O7 can be prepared also in a similar fashion like that of our calcium hydrogen phosphate. So, it is basically your diphosphate, and diphosphate can also be utilized from your calcium hydrogen phosphate, which we have prepared already from your calcium oxide, our corresponding compounds as the acid salt. So, next example what we will take is Na4 P4O7. That means you can have this, not NF-P4 is P2, Na4 P2O7, that means your diphosphate. So, diphosphate is basically we can have the POP linkage, and that POP linkage will have the double bonded oxygen also over there, and we can have these other groups also. That means you have this O as O minus, here also O as O minus, O as O minus. So, these basically when you have these sodium ions, so Na plus, so 4 such sodium ions will be present over there, and it is highly soluble in water because it is fully dissociated, because the sodium ions will go and it will be available and there is corresponding hydrated form of sodium. But if we use calcium, is basically can get in with this particular structure, so it can bind, quickly interact with these particular 2 oxygens to give you the corresponding calcium salt. So, this particular one in a similar fashion like that disodium hydrogen phosphate we take, again simple heating of this thing will give you, so 2 molecules of this will give you this plus water. So, heating of this particular one will give you this particular species. Similarly, we can have also the large scale production . What we can get, the large scale production, basically we can get it directly from phosphoric acid from the reaction with sodium carbonate. So, sodium carbonate will take care of these protons over there, and here the temperature is in the range of 450 degrees centigrade will be useful for this particular preparation. So, this corresponding one, that means the sodium salt, how useful this particular sodium salt is, therefore, that it can be utilized as emulsifier like that of our corresponding potassium salt, what we have seen, that it can be used as emulsifier, it can be used as a buffering agent, it can be utilized for thickening agent for food industry, thickening agent, and therefore it can also be a very good food additives, because additives are added basically in the food material to improve the corresponding shelf life or to stop the corresponding decaying of that particular food material. So, where we use these food additives, basically we use them in making chicken nuggets, in making pudding, and in storing the crab meat. So, these are very useful application of this material for our study, and where we see it also like that of our potassium salt, it can be used in toothpaste also, and making the dental floss. So, medical application also it has. So, dental floss, because it can be useful in controlling the tartar on our teeth. So, it is a tartar control agent, because why we get tartar, because we had the corresponding deposition like that of your in boiler material. We can have the calcium deposition also, because our food material, our other contents what we take, even in water we can have sufficient amount of calcium as well as magnesium. So, we can have both calcium as well as magnesium, which is also present in our saliva. So, that particular one can be removed. So, these metal ions can be removed from there, and therefore, in commercial dental rinses, basically where we get the commercially available commercial dental, what we call as the corresponding mouthwashes also. So, sometimes it is recommended that for this commercial dental rinses, before brushing we use this, we recommend to use this to reduce the plaque. So, it will be useful for plaque reduction. So, in all these cases what we see that our usual thing is that how we trap the metal ions like calcium and magnesium by some other material which is closely similar to that particular type of material which is already present in our toothpaste. So, if the toothpaste can have that particular material, it can also attack or it can also fight against the plaque formation or the controlling in the tartar in our mouth. So, it can be useful for our mouthwash as well as for our dental rinses. So, the next one what we can see is the tri one, that means NF5P3O10, which is the corresponding triphosphate, and is commercially it was prepared from industry level. So, it is basically the company what we know, the Tide, which is making the huge amount of detergent. So, the Tide is the registered trademark for that. So, Tide R. So, Tide is making, and they were working on it from say 1947, where it can be very much useful for this getting this particular one as your triphosphate. So, how you get like polyphosphates and all, the thing is that you should know only that how many phosphorus atoms are present over there. So, if we have the 3, then we get the double bonded, all these will have the double bonded oxygen over it, and then we complete the tetrahedral site above this. So, why we get this Na5? So, you get O minus 1, O minus 2nd, O minus 3rd, O minus 4th and O minus 5. So, these basically, so you can have the huge amount of charge and all these things like our different biomolecules, what we all know that the very interesting biomolecules what we can have in our DNA and all other cases, the deoxyribonucleic acid. So, they can be giving us ATP molecules, and these ATP molecules are the triphosphates. So, they can go for releasing one phosphate groups giving you adenosine diphosphates. So, getting all these conversions even in our body also, we do all the time the conversion of the phosphate to diphosphate to triphosphate and again back to diphosphate or the monophosphate. So, all these reactions, that means the phosphate formation and its condensation reactions are very much useful for this commercial application as well. So, this particular one can also very good for controlling the pH of the medium. So, for a pH it can control in the range of say 9 to 10, which is very much useful. So, is the alkaline medium, so it is not acidic basically. So, alkaline medium of pH is there. So, another interesting compounds what we will be seeing now, that going from these esters and all these things, we will come back again if we just consider this thing. Before that, if we just simply see how we get a one more compound which is also very much commercially useful, and it is prepared in a huge scale, on a large scale. So, it can also be a precursor for different types of organophosphorus compounds. So, organophosphorus compounds. So, if we want to make this, because these are very useful compounds, organophosphorus compounds, the name tells us that you can have some organic part to it, and that organic part basically, therefore, we can have a palladium carbon bond, phosphorus carbon bond. So, this phosphorus carbon bond will give you this particular cases, that means organophosphorus compound, but in some cases we will see that when we talk about the esters, instead of these, that means you can have at one end instead of PO minus Na plus, this is your O minus Na plus, because these are all your Na plus for your charge balancing thing. So, if these are from some organic part, that means the alcohol part is giving you the ester. Sometimes in a loose fashion, we also consider these as organophosphorus compound, since a organic part is attached to this phosphorus through oxygen, not a direct phosphorus carbon bond you have. So, truly speaking, the organophosphorus compounds should be like your different organometallic compounds and all other cases that you can have direct carbon to metal bond. Here you can have the carbon to phosphorus bond. So, if we are able to substitute this, that means around this phosphorus. So, if we can have this, that means if we are able to make say PMe or some phosphorus carbon bond it, then we can consider this as a typical organophosphorus compound. So, it can be the typical precursor for a precursor. So, therefore, this PCl3 is the precursor for the different types of organophosphorus compounds, and we get it very quickly or very easily by reacting elemental phosphorus, which we write most of the cases as P4, or sometimes we can write it also as P2. So, P4 plus 6Cl2. So, if we pass the chlorine gas over it, it is basically converting it to your 4PCl3. So is basically going for evaporation. We evaporate it, and from that evaporation, if we go for condensation, we get back this particular PCl3. So this particular one, as this is applicable on, say, typical source of this phosphorus is your white phosphorus, and we take it as a suspension. So suspension of white phosphorus we have, and we pass the chlorine gas. So when chlorine gas is passed over the suspension of white phosphorus, we get this PCl3 in our hand, and this PCl3, making this PCl3 can have so many uses, and those uses are making H3PO3. We have not considered in detail of this particular acid. We have considered the phosphoric acid, but this is the phosphorus acid, where the phosphorus oxidation state is in +3. Then we can have the corresponding making of POCl3, which is another very useful reagent for the laboratory purpose, for industrial purpose also for making phosphoric acid, and the acid chlorides of fatty acids also, acid chlorides of fatty acid, even for the different organic chemicals, making the different organic chemicals also, the acid chlorides of fatty acids. That means this is a very good chlorinating agent. It can provide the chlorine to the organic molecule, converting this to particular molecule as your corresponding acid chloride. So when you have the thing as your CO2H, we get it as COCl, which is your acid chloride. So in this fashion, so the phosphorus trichloride. So from phosphorus trichloride, we get it as the corresponding one as the next compound, which is your PCl5. So this PCl5 is again we can have, and we can have also the PF3. So all these things we will be considering in our next class. But before going over here, so we just get this as how you get this PCl5. So is nothing but addition of one of the Cl2 on the PCl5. So when we get that, this basically as a product as sinks at the bottom of the reaction chamber, and which should be removed from there. So they are removed by a screw conveyor. So when you have the spiral screw type of conveyor, not the flat type of thing, so screw conveyor will be useful to take out that particular one from there, and this also can be useful. So application for this particular PCl3. So one such example is that if we use with some Grignard reagent, if we allow it to react with the Grignard reagent, that phenyl magnesium bromide, what should be the product? So if we can ask ourselves that what should be the product for this reaction, that means if we have the phosphorus trichloride and reacting with this, is basically giving us a very useful molecule, which is very useful ligand. So this is considered as a ligand. So this is our ligand, and this basically giving for the corresponding one for making this triphenyl phosphine. So is basically the 3 mg BrCl. So that 3 mg BrCl formation will give us, along with that of your triphenyl phosphine, which is your ligand. So we'll consider in our next class that how this particular triphenyl phosphine can be useful for making the different types of compound, because when this is your ligand, we can get the corresponding metal ion complex from there. So all these things along with will come back again for making this PCl5 and PF3. We'll just consider them, which one will be useful ligand, because we are in the intention of making some useful catalyst based on these phosphorus based ligands. Thank you very much.